This is our presentation for Computer Science 168, Deep Learning for Glaucoma Progression Prediction. This is Carol.
And this is Osama.
Here's an outline of our presentation. We will have an introduction for glaucoma, our proposed solution. We will explain the dataset, the method, the results, and finally a conclusion. First, as an introduction for glaucoma, it is an eye disease that results in loss of sight. It is the second leading cause of blindness worldwide. The number of people affected is 60 billion in 2010 and will reach 111 billion in 2040. Glaucoma is caused by increased pressure in optic nerve, and it is characterized by structural variations in retina. Retina structure is imaged by optical coherent tomography, which is short for OCT. The picture below shows the difference between the normal eye and an eye affected by glaucoma. Since early detection of structural variations facilitate treatment, we want to predict the progression of glaucoma at early stage rather than waiting for this progression to happen. To achieve this, in our project, we use a learning-based generative model to predict this future retina structural variation. The model input is 3 images of subsequent time points, separated by 6 months, and the model output is a constructed image of the following time point. So now we will introduce the dataset. The picture on the left shows the hierarchy of the dataset, and the picture on the right is an example of the cross-sectional image. OCT images of patient retina are in the dataset, and we use the left and the right eye independently. Each eye image is recorded at 4 to 10 different time points with a 6-month gap. Each of the time points will have 62 cross-sectional images of the macular area. And we have no assumption about the baseline, which means all patients have glaucoma at various stages.
Our generative model, we used conditional GANs, Conditional Generative Adversarial Networks, or for short, CGAN. Generative Adversarial Networks are generative models that automatically learn the loss function via an adversarial mechanism. It consists of 2 main parts, a generator and a discriminator. The generator generates images, and the discriminator evaluates the generator output. We further used conditional GAN, and in conditional GAN, or for short CGAN, we feed the input to the discriminator with the real or fake images, and they are concatenated together. We do this because we want to condition the output of the GAN network on the input images to constrain our predictions more. The generator consists of 2 parts. The first part is 3D convolutional layers to learn the spatiotemporal features. Since our third dimension is time, we want to capture the features over time as well. The second part is a unit-based architecture. It's a decoder-encoder network, and we have skip connections in the decoder-encoder architecture to copy the learned features between the front-end and back-end layers. The second part of our network, the discriminator, it's a patch GAN-based architecture based on fully convolutional neural networks. It doesn't classify the image as a whole, but instead it looks at patches and classify them independently. The purpose of that is to preserve the structural content. To evaluate the output of our network, we measure the thickness at 3 locations and compare those thicknesses between the ground truth and the generated images. We picked those locations based on glaucoma experts' recommendation on 3 locations, which are the nasal peak, the pit, and the temporal peak, as shown on the image on the right. In this slide, we summarize our results. We have plotted the relative error against the sample indices. We made total of 38 predictions for 8 patients at multiple stages of the disease. The maximum relative error between the ground truth and the generated images was about 3%, and the measurement error of our method was also around 3%. Hence, the thicknesses of the ground truth and the generated images are in good agreement up to the measurement error. In conclusion, conditional GAN has strong potential for success in glaucoma progression prediction, and we were able to predict retinal cross-section that shows glaucoma progression in 6 months. The thicknesses of the cross-sections of predicted images match the ground truth up to the measurement error, and the limitation of our method that we sometimes got artifacts that might exist in the predicted images, but this only happened in 4 images out of 38 predicted images. Thank you.